So today we're going to cover impulse and linear momentum. Okay. So what do you guys, when you hear the word momentum, what is the first thing that comes to your mind?
Going faster.
Going faster.
Like you're gaining momentum.
Gaining momentum. Yeah, gaining momentum is going faster, but just momentum.
Energy.
Energy. Yeah.
Like past energy fueling future energy?
Past energy and future energy. Okay. So, you know, remember the first law of Newton? What was the first law of Newton?
An object in motion stays in motion. An object at rest stays at rest unless acted upon by
Yeah. It's that kind of resistance, right? Resistance to start a motion and resistance to stop, right? So, momentum is another way to measure this difficulty to change, okay? That in a motion of an object that relates the mass and the velocity, okay? Let's see if I can show you an example here. I'm going to show you different scenarios. So observe what happens. So I have two cards here. They have about the same mass, okay? And at this point, here, I'm gonna do a little push, right? That's what we did on our first experiment. We talked about this push. We never said anything about force, right? We never mentioned anything. We just said, do the push and see what happens, right? So now I'm gonna do this push, and we're gonna concentrate on what's happening at this. So the push is like that, and the card is going away, right? And first, how long you think this push was?
time-wise or
Yeah, time very short, right? It was just touching the card, right? Seconds. So so we call this here momentum is the product of the mass times the velocity. So if mass is a scalar, velocity is a vector, a number times a vector is another vector, right? So momentum is a vector, okay? So that's one thing to observe. The other thing is when we talk here about delta P, that's the change in momentum, right? Is mass times the change in velocity. Okay? Now, velocity divided by the time is the acceleration. When I plug that in here, what is that I have? I have now MA. MA is the force. Now, force times delta T is equal to this momentum here, right? And we call this the impulse, right? When we talk on this side of the equation, force times the time, we're talking about impulse. And that's what I mean by this push that I gave the card at first, okay? This is the impulse part. Now, when it comes to this collision here, that's the momentum part of it, okay? So, and what is that happens here? Tell me, what do you think is happening here? When I push this and goes that way.
the energy is being transferred once it hits the other card.
It transfers, right? And so this is what we call an inelastic, I'm sorry, this is what we call the elastic collision, right? It goes right away there, right? Boom, right? Transfers right away. Now, let's see what happens if I put some weight on the car. Okay, I just put 2 bars here. So let's see what's going to happen. Now, what do you think is going to happen?
You won't move as far.
It won't move as far. Which car?
The one of the weights.
This one is not going to move as far. So let's see again. So it's here. And I send this guy and goes. What happens to this guy? Stop. And this guy move. Do you think the speed is about the same as this one here and the other one? It's about the same, right? Let's see. Let's try very slow. It's going very slow, right? If I try faster, it goes faster. Everybody's okay with that, right? So now let's put this weight here. And then you said it's going, the first is going to back. Is that what you guys think? And this guy, what's going to happen to this guy? We'll move forward, right? So let's see what happens. Move back. Let's try now at the slower speed. Yeah. Let's put more weight now and see what's going to happen. Let's try with the slow speed first. So what do you guys think? This guy moved forward but much slower, right, than this guy. Let's go with our fastest speed. Oh, that was too fast. Well, experiments sometimes, don't work, right? So let's do it again. I want to do a little faster. Maybe I have somebody there because I'm afraid this thing's going to... Anybody wants to be there? And you're going to be on the video. Is that okay? Okay. So just put your hand there so it doesn't... just put your hand like this so the car doesn't go away. So let's see. Let's put this there. I'm going to try to do this really fast now. So this came back faster and the other one was slower. Is that clear now to everyone? Very good. So that's one thing I wanted to show. That's the momentum part of this problem. The other one is this little push, right? That I give, right? Now, why is this impulse important? So I'm going to try to demonstrate that with these balls, right? So this one here and this one here, I'm going to let them go, and you guys tell me what is the difference. No difference.
One percent.
This one here was bouncing, right? More than this one. Let's do it again. So this one just came and almost stopped. My objective was just to come and stop right away, right? Because it still have some air here, right? It didn't go straight. This one here has more air, so it bounced out and slower. So what do you think in terms of force and time? Which one you think change motion faster, change momentum faster? Which one?
Probably the red one.
The red one?
It's changing like
It's
momentum.
changing momentum from here. What is the change in momentum? They both the same mass. I let them go, at the same position, okay? What was the change in momentum between those two balls? Is this one more than this? Is this one more than that one? Or are they the same? The change in momentum. Momentum, remember, is mass and velocity, right? So if I have this car going, it has some momentum. It has the mass and has the velocity. And then transfer to the other one, right? But there was no change in momentum here. The momentum was this way, right? It's the same. This is the initial velocity of this car, is 0 right now. I have this car going at a certain constant speed, right? There's no friction, assuming there's no friction here. It's going at constant speed, has some momentum, and the final momentum is this mass times this velocity, this mass times this velocity, that's 0. So the momentum was conserved. Do you guys see that? Before the collision and after the collision, the momentum was conserved. It's the same. Okay? Momentum is always conserved. Now, there is a different situation that I didn't show. I'm going to show you now. It's this one. Look. Pay attention to this one. This is interesting. The car is going. Is this one called the inelastic collision, right? Because now what happened is, before was like that. I had this spring here. It will transfer the other way. But this time here, it's sticking together, right? Still, the momentum is conserved here. The speed of both is the same after the collision, but the mass has changed, has doubled. Okay? Now, here what I'm asking you about is, how is this, the momentum here, did the momentum change here between these two guys, or are they the same?
It must be different, I think. That ball keeps on bouncing, but that ball just stops.
Same, but not during the bouncing. I'm saying at the end. At the end, it start here, it's end there, right? It's just that this here is taking a little longer, right? But in the end, it's going to stop there at the same position, right? What is different between these two guys is this part of the equation. So what is the difference? If the momentum is the same, so this part is the same, right? But there are different situations between these two guys. And what is the different? What is different? The time. So if it takes longer to get to a stop, what is happening to the force? If this is a constant, if it takes longer, what happens to the force? Yes.
It would be a larger amount to compensate for the, or a smaller amount to compensate for the larger time.
Small. You guys see that? This thing is constant. If the time goes up, the force goes down. Right? If this is very short, the impact is stronger, right? It stopped immediately. It's like, you know, other than doing like this, right? If I push my face like that, it's one thing, but if I just do like that, it hurts, right? Because the force here, it takes longer, little by little. here is at once, right? So what kind of situation you think this is important? It's a safety issue. What do you guys think?
When you're testing cars, like you're trying to find out what happens when they get into a wreck.
Yeah, so when you design a car, which situation you want? You want this situation or this situation? Right? You want to take it longer, right? So, so those are parts of my notes. I'd like you guys to go through it. I have the example of the bouncing balls explained here. I have example of the car crash, right? They actually do this test. They measure how long it takes to go to a stop when the car is coming to a wall. And the longer it takes, the better. So I have a problem here that asks you to calculate the force on the car and the force on the passenger. The passenger takes longer because it goes forward, comes back. So the force on the passenger is less than the force on the car. So you're going to do that calculation at home, okay? And if you don't understand, we can go over next class. And I have problems, example with numbers. I don't have time to go through here, but I'd like you guys to go home and do this. You have to do this as part of the class. We just don't have time. And then we do some analysis, like the demonstration that I have here with the calculations of the momentum, okay? Maybe, so let's just make a little, so I have here, let's say I have here mass, and I have here another mass. This is M1, this is M2. M1 is going with a certain speed, V1, M2 is with V2. That's another thing that I can do also. I can have, instead of the car to be here, at rest, I can get the car to move and then I have the other one moving. So the general situation is that we have both masses moving, and then one can collide with the other one, and we can analyze that momentum. So this is before the collision. Right, I'm driving, there's a guy in the front, he's going slowly, but I'm going faster than him. So at some point I'm going to hit him in the back. It's my fault, I know. But the collision was inelastic, so now once I crush it in his back, you know, we keep moving together, you know. Right? Keep moving together. So that's going to be, now the speed is going to be the same because we now are together. Remember that example I had here? There I had the car and then they moving together, right? So the speed is the same. But now I have M1 plus M2. So how do I write this equation for the change of momentum? So momentum of the first one, M1 V1 plus M2 V2, is going to be equal to what? Before the collision and after the collision. What should I write here? This is after the collision. What is momentum? Huh? P. But P is
Mass times velocity.
mass times velocity. What is the mass now? M1 plus M2. The velocity is the same, so I'm going to call V prime. I call this line here always after collision. okay? So in this case, it's inelastic, right? So I would write that way. If it were elastic, then I would write my momentum equation, M1 V1 plus M2 V2, and is that gonna be equal to what? M1 V1 prime plus M2 V2 prime. Okay, this is for the elastic, this is for the inelastic. And you need to pay attention to the directions, right? Because this is a vector, so you need to pay attention, you know, if it's going positive or negative. And okay, I think I'm going to stop here. I think this is enough for you guys to do the experiment today. So let's try to do that, and I will restart next class, you know, this part again. Okay, is that okay? All right, so